Yeah.
Okay, so good afternoon. Today I'll talk about smart roads, system for development and comparison of algorithms for solving vehicle routing problem with realistic constraints. So the task of vehicle road optimization is class of combinatorial optimization problems. We have their main task to find the optimal path between customers and suppliers on the map, taking account various restrictions. We know that this problem has many real-world application like goods delivery, distribution of goods between depots and stores, web internet package routing, and others. In practice, there are requirements related to business that needs like real-world constraints, real-world restrictions. For example, the volume of customer goods should not exceed the capacity of the fleet of the vehicles. Time windows for delivery should be delivered in convenient time, and for example, we should have the ability to both deliver and pick up goods from customers to stores and otherwise. And of course, the main problem is kind of growth of business, which follows to growth of problems, and we have to solve problems with large size, like more than 1,000 points. Today, we have kind of three main approaches to solve this problem. Two of them belong to kind of classical one. First of all is integer programming. Here we have theoretical guarantee to have optimal solution, but of course we have exponential time complexity. So there follows that we can't use it like on the large size, because it kind of follows to unlimited time to solve problem, to optimize problem. The second classical approach is heuristics. Here we have a reasonable time to solve problem, but of course no theoretical guarantee to get optimal solution. And of course, heuristics requires kind of domain knowledge, which follows to kind of large time to develop new one. And of course, problem to develop heuristics for new restrictions, for new problems. The third one is kind of new approach to solve road optimization problem is neural networks and deep reinforcement learning. Here we have better time and better results, but of course there are still no theoretical guarantee. There are still more approach, but we still don't have any pipelines to compare different approach on different data sets and choose the best one. So that's why we are trying to present our research, our work. But let's talk more about pipelines. Two examples of classical approach, as well as baselines of current work. LKH3 is kind of classic local search heuristics used in many research papers as baseline, as strong baseline. Here, first we find like feasible road and trying to optimize it by swapping subroads and try to find the better result. It appears back in 1933, but there are still many articles which come in every year and trying to optimize like solution quality and time quality. Second baseline is ORTools. It's open source solution from Google. Here we have first approximate solution by meta heuristic of small classical heuristics and local optimization by OR search. This tool used for many production solvers because it's because it's open source, of course, and we still have it. It still can work from out the box. For the integer programming and exact solution, we used the SCIP framework, which has many classical integer programming approach to solve route optimization problem and supplied under different licenses, and we used academic one. About reinforcement learning approach, they're generally divided into three types. First of all, based on iterative pass construct step by step, we use a transformer encoder to encode information about current road and, for example, current capacity of our fleet, to encode it in latent space vector. And with decoder, we trying to build our route step by step. Classic basic first approach of JAMPR used additional masks in latent space to filter feasible and unfeasible solution, but there are still many upgrades on this. Second reinforcement learning approach named learning to improve, and it's kind of class of approaches that trying to build learnable neural heuristics like classic one, but with additional network information, with additional learnable network heuristics. And the main approach here is to optimize with predefined steps the first feasible solution. The third and the latest one is approach based on dividing roads on the sub-roads and trying to optimize a small part of task with classical approach. Of course, all of three of them have their own pros and cons. But as I said, we're trying to solve realistic constraints. That's why we're trying to build our solution on the JAMPR strategy. Here we're trying to add additional learnable masks on the road, on the policy of network. It's kind of learnable mask that just multiply the output policy, the output probability to go to the next point from current one. Let's talk maybe more about data which we are used. All experiments we are carried on the generated data from the Salmon distribution is kind of classic data for the problem of vehicle road optimization. Here we have 1 by 1 square. The points here are uniformly distributed. Distance between them are Euclidean distance, and each client's cargo has weights from normal distribution with predefined parameters. We have time windows with the same normal distribution, but clipped with different values, predefined values. We tried to carry two type of experiments on the small 50 points and kind of medium one size points, 100 points. All instances are CVRPTW instance of problem with soft formulation. It means that we let algorithm to skip clients, but penalize the result with number of missed clients. We are trying to optimize weighted sum of total path lengths and penalty, which I mentioned above, and we count in the end the gap between the best solution on the 1,000-second optimization graph between the best solution, all algorithms, and current one. Let's maybe talk more about our system, smart roads. There are three main parts. Three key parts: data set, the data part, algorithm, and solution. All modules communicate with gRPC protocol and have their own goals, and try to say about it with little more details. Dataset, data model responsible for generate data with predefined parameters of generation, allows to load your own data and, of course, previously created ones. Dataset knows how to convert data from user to internal system formats and stores information about data in the database. We use NeuroIPS or tech data format as input in our system. I'll show it a little bit later. We use this because it's kind of common one for road optimization competition, latest one. That's why. So algorithm model divided into two parts. It's training and inference. Training, of course, relates to neural networks, while prediction or inference use, of course, any type of algorithm. Every algorithm in inference written on C++ with conversion of PyTorch model to scripted one. Here we have additional interfaces to, if you want to add your own custom algorithm, custom solver, just implement interfaces and you can use them in system, in our platform. Solution model responsible for visualization, responsible for web interface, for presentation of our platform. Additionally, solution part knows about metric, how to count metric, calculate metric, how to visualize it, how to compare it. Of course, there are interfaces to implement your own metric and calculate it. So useful one. A little more about this visualization. Here, how platform looks like. In the train page, we set, as I said, parameters for training network. Right now, we support only JAMPR-like networks, so of course parameters only for them, but later it will be updated with your own structure, your own architectures. Inference part. Here you can choose the type of problem, the type of restriction, the type of data set, the type of metrics, and other one. Just tick submit and you will get metrics which I ticked before. And about data and data generation. We have, as I said, format of NeuroIPS or tech format. It's on slide. Here you also can place numbers of your distribution, and the dataset will be generated. Let's see experiment result, which fully got from our platform. Here you can see dependence of gap percentage from time limit of optimization. You can see that neural networks and ORTools solvers kind of gain the same result, which is less than 5% worse than exact approach. But you can see that exact approach based on SCIP solver only shows the first results on 40 seconds of optimization. If we talk about 100 points, here the same results on ORTools and JAMPR. We have the same suboptimal solution in the first seconds and kind of approximate the same result on the end of this 1000 seconds. But what's interesting is that SCIP exact solution kind of show the first result only after 1000 of seconds of optimization. So it seems kind of unuseful for realistic tasks. Here we can see all results on the same graph, and this blue box marks the area of applicability of exact approach. So if we have enough time, of course we can get the better result. But if we limit it in time as it happened in real tasks, of course the left zone from the orange line of SCIP is good for classical heuristics or learnable neural heuristics. In the end, we conclude that for the size of 50, the neural and classical heuristics close to SCIP, close to exact solution, which means the choice of model mostly depend on the restriction of the maximum optimization time of the problem. The same result is for size of 100 for the medium size of task, where we have the first feasible SCIP solution about 13 times slower than heuristics one. So that's all. Question, please.
Okay, thank you a lot. Do we have questions from the auditory or from online auditory? Okay, maybe I have several questions. So, as I understand, the results of your work is some test bed to test some machine learning algorithms for solving this vehicle routing problem. And the results of comparison, some algorithms. Am I right?
Yes, on this platform. Yeah.
Okay, and so what is the idea behind this platform? So
basically, as I said, we have many.
Yeah, I realize I'm trying to formulate, and then you can guess whether I'm right or not. So probably you are yourself working on advancing some algorithms for solving this problem, and you would like to have this test bed to test your ideas. Am I right?
Yep.
Okay, that's fine.
And not only mine, because I'm trying to open source this project, and if you want to see it, you can just write me on my email and I will share it.
Yeah, okay. But okay, within your architecture, as a part of the algorithms, you do have. So you presume that you would like to test only machine learning algorithms. For instance, in our previous talk, we heard about generic algorithm. Is it to insert somehow algorithms that are not based on machine learning and compare the results with the machine learning algorithms.
So yes, there's still no genetic algorithm in my platform here, but because we try to scale on large size and placed all our attention to large size only, but I can say that the next our step is just add genetic heuristics to our platform and compare with them.
Okay, thanks a lot. Do we have more questions? Okay, actually we have plenty of time, so maybe the last question. So maybe I missed something, but could you please give some details on what do you mean by realistic constraints? So you presume that there are some constraints and there are some realistic and non-realistic constraints. Could you
Yeah, actually, I said about time windows and capacity of fleets because it's kind of main, how to say, a restriction that faced in real-time problem in real-time routing optimization. And by saying about real world constraints, I'm saying about capacity, I'm saying about time windows, I'm saying about pickup and delivery. So where we want to pick up and deliver, I mean, from the pods and not only pods, from the users too, from the clients too. So these three is kind of realistic ones, I hope.
Okay, thank you a lot. Okay, so if we don't have any more questions, so thank you a lot for your talk.